December 6, 2025, the James Webb Space Telescope, accompanied by the quiet undercurrent of expectation, turned its instruments toward a newly arrived interstellar object. Scientists anticipated familiar chemical signatures. What they found instead was deeply unsettling, roughly 95% carbon dioxide and only about 5% water. The result registered as a 4.5 sigma anomaly, a level that strains and ultimately breaks every established comet model. Peer review described it as something never seen before. NASA's public statements sounded calm and procedural. Yet the telescope's own data told a far more troubling story. The question became unavoidable. What exactly is out there? And what else refuses to make sense? Numbers have no opinions. The James Webb Space Telescope returned a spectrum from 3I Atlas that forced researchers to stop, then verify, and then verify again that nothing had gone wrong. Calibration checks were repeated. Instrument settings were scrutinized. Nothing changed. The chemical signature of the coma was not merely unusual. It was stark. In most comets, water vapor dominates the signal by a wide margin. In this case, carbon dioxide overwhelmed everything else. This was not a slight imbalance or a statistical oddity. Measurements showed carbon dioxide exceeding water by at least 8 to 1, with some analyses suggesting an even greater disparity. Peer-reviewed reports described it as one of the highest carbon dioxide to water ratios ever recorded in any comet, whether from our solar system or beyond. The details are unambiguous. At a distance of 3.32 astronomical units from the Sun, the NIR SPEC instrument aboard JWST captured emission lines where carbon dioxide rose prominently above the background. Water, normally the defining feature of a cometary spectrum, barely registered within the framework of comet science. This is not simply rare. It sits far beyond the expected range. The technical papers avoid assigning a single precise percentage, but the agreement across analyses is clear. 3I Atlas falls well outside the bell curve of known comet compositions. Researchers tested error margins and systematic effects repeatedly. They re-extracted the spectrum using different physical models, adjusted aperture sizes, applied alternate continuum fits, and ran extended source calibrations. Every approach produced the same conclusion. The result was stable. The data did not shift. Carbon dioxide, not water, was the dominant volatile escaping the nucleus. For decades, comet scientists have compiled chemical inventories for hundreds of objects, from Jupiter family comets to long-period visitors from the outer reaches of a solar system. Against that backdrop, 3I Atlas occupies the extreme edge of the distribution. Official analyses note that such a composition implies formation or processing conditions unlike those found in our solar system. This is not a small correction to existing theory. It is a spectrum that stands apart and demands explanation. The numbers are published, and they are not going away. Peer-reviewed journals rarely use the word unprecedented. In this case, they did. The published analyses describe the spectrum of 3I Atlas as chemically unlike anything previously documented. Carbon dioxide dominates the coma, relegating water to a secondary role. This goes beyond curiosity. It directly challenges the models that have shaped comet science for decades. Researchers have long relied on a well-established chemical pattern, water first, with carbon dioxide and carbon monoxide trailing behind. 3I Atlas reverses that expectation. Official summaries emphasize that it represents one of the highest carbon dioxide to water ratios ever observed in any comet, solar system or otherwise. What does that imply about its origin? The papers do not rush to definitive answers. Instead, they outline scenarios that stretch beyond familiar ground. Perhaps the object formed near a carbon dioxide ice line in its parent system, where CO2 could freeze while water remained gaseous. Or maybe it spent vast stretches of time exposed to interstellar radiation, with cosmic rays altering its outer layers in ways not yet fully modeled. Both ideas are plausible, yet neither fits comfortably within existing frameworks. The implications are not limited to theory. If standard models fail to explain this spectrum, then assumptions about interstellar chemistry itself come under scrutiny. The language in the literature is careful, but the implication is unmistakable. This is not a minor outlier. It is a data point that does not fit. As one peer-reviewed summary states, These conditions are unique compared to those present in our solar system. That phrasing is deliberate. It signals that something fundamental may be missing from the current picture. Spectral analysis leaves little room for interpretation. The raw observations from the Very Large Telescope and JWST tell a straightforward story. Nickel is present. Iron is not. Each emission line appears at a precise wavelength, as distinctive as fingerprints. Nickel shows up clearly in both near-infrared and optical bands, with multiple lines matching known transitions of neutral nickel. At the same time, iron lines that should normally accompany nickel in a cometary spectrum are absent. They are not merely weak. They do not appear at all. Even in deep exposures and after careful removal of dust contributions, the identification process follows strict procedures. Observed peaks are matched against laboratory line lists, with checks for blending, overlap, or instrumental artifacts. In the case of 3I Atlas, the nickel lines rise well above the noise. They are confirmed in repeated observations taken at different times and with different instruments. The missing iron is not a calibration mistake. Analysts compared the data against skylines, reference stars, and the known response of the instruments themselves. The conclusion remained unchanged. In comet science, nickel and iron usually appear together. Both are refractory metals forged in similar stellar environments, locked into comparable minerals, and released through related processes as a comet warms. 3I Atlas breaks that rule. Nickel appears alone, without iron, until the object moves much closer to the Sun. This is not a subtle effect. Iron's characteristic lines are simply absent, even as the nickel signal strengthens with decreasing distance. The data are publicly available. Anyone can access the archives, overlay atomic line positions, and see the pattern directly. The nickel lines are real, persistent, and clearly separated from the background. The iron lines remain missing, even after stacking exposures and pushing the signal-to-noise ratio to its limits. These are not artifacts of processing. They are physical features recorded in the light from an object passing through our solar system for what is likely its only visit. For researchers, the task ahead is obvious. Explain how a comet can emit nickel without iron, and why this pattern changes only as it approaches the inner solar system. The spectrum provides the evidence. Interpretation must follow. Avi Loeb's reputation ensures his voice is not ignored. For years, he has urged astronomers to take anomalies seriously, particularly when interstellar visitors refuse to conform to expectations. With 3I Atlas, the measurements alone already strain existing ideas. Loeb's commentary sharpens the debate. He does not point to a single definitive clue. Instead, he asks why. After decades of comet research, scientists continue to encounter signatures that resist natural explanations. In interviews and opinion pieces, he draws parallels to the debate surrounding Oumuamua, reminding colleagues that spectra do not always clearly separate natural from artificial origins. When chemistry falls this far outside the expected range, he argues, all explanations deserve consideration, including those that make people uneasy. From his perspective, the carbon dioxide-dominated coma and the unusually early activity are not trivial quirks. They highlight how narrow assumptions about interstellar objects may be. He warns that science often gravitates toward familiar answers even when data point elsewhere. As he has said, nature is under no obligation to behave consistently. His concern is not that 3I Atlas proves technology, but that the scientific process risks failing when outlier data are dismissed too quickly. If an object from another star system exhibits chemistry described by peer review as unique compared to our solar system, then it warrants deeper examination, not a hurried fit to existing models. This is not an argument for conspiracy. It is an argument for rigor. Loeb has repeatedly emphasized that limiting explanations too early risks overlooking rare signals. In the case of 3I Atlas, he stops short of making claims. Instead, he frames the anomaly as an opportunity to probe the boundaries of current understanding and to consider whether unfamiliar processes might be at work. The discussion remains open. The evidence is available. The real danger is not being wrong, but failing to recognize when nature presents a puzzle from outside the expected set. TESS first detected signs of activity from 3I Atlas on May 7, 2025. At that time, The object lay about 6.4 astronomical units from the Sun, nearly twice Jupiter's distance, in a region where sunlight is weak and water ice should remain solid. According to standard comet physics, water-driven activity should not begin until much closer, typically within 3 astronomical units. Yet photometric data revealed a faint but persistent glow around the nucleus. It was not a brief outburst or random spike. It was a steady signal that gradually intensified over time. Astronomers examined the light curves closely, searching for alternative explanations. The brightness. Variations were not random. They showed repeatable patterns consistent with a rotating, active body. One producing jets or plumes of gas and dust. Rotating jets, operating at 6.4 astronomical units. At that distance, solar energy is insufficient to trigger water sublimation. That left only more volatile ices, such as carbon monoxide and carbon dioxide, as plausible drivers of the activity. Even so, sustained outgassing at such a distance remains rare, even among the most unusual comets. Surprise! Comet researchers went back through archival records searching for anything comparable. A small number of long-period comets had shown faint signs of activity beyond 6 astronomical units. But those cases were rare exceptions. In most instances, the signals were weak, barely distinguishable from background noise, and often explained by cosmic ray interactions or internal cracking rather than direct solar heating. For 3I Atlas, the data pointed to something more coherent. The photometric measurements revealed a low but unmistakable level of continuous outgassing that persisted for weeks as the object slowly moved inward. There was no ambiguity. The initial detection was not a one-off. Follow-up observations confirmed the presence of a faint coma, and ground-based telescopes measured dust production rates ranging from roughly 0.3 to 4.2 kilograms per second in July. Those values placed 3I Atlas among weakly active distant comets. The real shock was not the scale of the activity, but its timing. The activity began far earlier than expected, at a distance where most comets remain inert. This early onset forced astronomers to reconsider long-standing assumptions. If 3I Atlas could release material at 6.4 astronomical units, then either its surface was rich in extremely volatile ices, or its chemistry and internal structure differed fundamentally from the standard comet model. The data alone did not resolve that question, but it established the context for everything that followed. The object was active before the Sun should have been capable of driving that behavior. For this visitor, the rules were already being stretched. Sunlight barely reaches the outer regions of the solar system. Yet 3I Atlas showed activity long before it approached the Sun. Early photometry and imaging campaigns captured a faint, persistent plume extending sunward, suggesting a directional outflow rather than the irregular spray seen in some comets. By late August 2025, the anti-solar tail extended to about 56,000 kilometers in projected length. While not unprecedented, it was clearly detectable. This was a structured release of dust and gas occurring at distances where water ice should remain frozen beneath the surface. Ground-based observatories followed the evolution of the coma night after night. Optical photometry again yielded dust production rates between 0.3 and 4.2 kilograms per second throughout July. These measurements firmly place 3I Atlas within the category of weakly active distant comets. It was more active than astronomers initially expected for an interstellar object, yet still modest compared to the most prolific comets known. Gas measurements in the submillimeter range from the James Clerk Maxwell Telescope detected hydrogen cyanide outgassing at roughly 2 kilograms per second in September. When all contributions are combined, the total mass loss remains on the order of only a few kilograms per second. Over the course of a month, that amounts to a few million kilograms, far from the kind of rapid erosion that would destroy a comet in a single solar passage. Again, the surprise lies not in the quantity, but in the timing and composition. Activity began at 6.4 astronomical units, well beyond the distance where sunlight can drive water sublimation. Standard models predict a largely dormant surface at such ranges, with only the most volatile ices, such as carbon monoxide and carbon dioxide, capable of escaping. Yet the outgassing persisted and intensified as 3I Atlas moved closer. Spectral imaging from the James Webb Space Telescope mapped a sunward jet dominated by carbon dioxide emission, confirming that the activity differed chemically from the water-driven behavior typical of inner solar system comets. Images from Gemini South and the Very Large Telescope showed a compact coma and a clearly defined anti-solar tail, but no evidence of massive, highly collimated jets extending hundreds of thousands of kilometers. The observed plume, tail, and coma fall well within the normal range for volatile-rich distant comets. What makes this object stand out is not the scale of its activity, but its persistence and unusual composition at such large distances. Astronomers searched for signs of violent outbursts or sudden brightness spikes. Instead, they observed steady, low-level erosion, dust and gas flowing away in a controlled, sunward pattern. There were no explosive events and no rapid mass loss. The data point to a stable nucleus gradually shedding material and responding to solar energy in a way that bends established expectations without completely overturning them. The picture that emerges is consistent. 3I Atlas is not being ripped apart by its encounter with the Sun, is quietly active, losing mass at rates comparable to the most volatile-driven comets known, but with a chemical makeup that sets it apart. That contrast leaves an open question. Why does this interstellar visitor, with its carbon dioxide-rich jets and unusually early activity, behave so differently from the textbook model of comet evolution? The measurements are precise. The image is archived. The discrepancy is physical, not semantic, and it cannot be dismissed as a calibration problem or observational bias. NASA's official statements have been restrained, almost deliberately calm. Briefings and press releases describe 3I Atlas as an interstellar comet that is notable but not alarming. The language emphasizes scientific opportunity rather than surprise. Public summaries stress that the object poses no threat to Earth and is broadly consistent with expectations for a comet originating beyond the solar system. The focus remains on the rarity of the observation, the value of studying a visitor from another star system, and the promise of new data. When questioned about the composition, NASA representatives highlight the importance of expanding our understanding of comet diversity. The official position is that comets can contain different mixtures of ices and that interstellar objects may simply reflect the range of conditions present in other planetary systems. Technical releases maintain the same tone. The carbon dioxide-rich spectrum is described as unusual, but still physically plausible. NASA's communications emphasize learning about the building blocks of distant systems. There is no talk of broken theories or looming crises. The message remains measured and steady. 3I Atlas is often framed as a glimpse into the chemistry of the early universe, an opportunity to compare the comets of our own solar system with material formed elsewhere. The emphasis stays on continuity, on how each new observation expands an existing catalog rather than overturning established rules. In public question and answer sessions, NASA scientists respond to inquiries about the object's orbit and behavior with steady confidence. The trajectory is hyperbolic, confirming its interstellar origin. Its activity, while notable, is explained as a natural response of volatile-rich ices warming under sunlight. The official narrative centers on curiosity, not alarm. There are no extraordinary claims or ominous warnings, only reassurance that science is proceeding as expected and that each new data point adds clarity. The public message is consistent. 3I Atlas is a rare and valuable visitor, not a sign of cosmic upheaval. Technical reports and public messaging, however, rarely speak in exactly the same voice. In the case of 3I Atlas, that difference is particularly noticeable. Official NASA briefings rely on broad descriptors such as unusual, interstellar, and diverse. Press releases emphasize the excitement of discovery and the chance to study an object from another star system. There is no reference to statistical extremes or theoretical limits being tested. Instead, the tone remains even. This is presented as a comet, richer in carbon dioxide than most, but still within the bounds of physical possibility. The technical literature is more exacting. It speaks in ratios rather than sound bites. The James Webb Space Telescope NIR spec team describes a coma dominated by carbon dioxide, with water vapor present but far weaker than in the vast majority of comets studied so far. The published analyses avoid pinning down a single percentage. Yet the measurements sit at the very edge of the known distribution. Phrases such as "among the highest ever measured" and "unique compared to those present in our solar system" appear in print. These are not chosen to reassure the public. They are cues to other scientists that the data does not follow the usual pattern. Nowhere in the public-facing material does NASA discuss how far these values lie from the norm. There is no mention of standard deviations or of how rarely such a composition has been observed. The technical summaries, by contrast, quietly document the anomaly. They detail calibration checks, repeated data extractions, and systematic tests, each confirming the same outcome. The numbers are present, but the wording is restrained, almost coded. The contrast between press conferences and journal articles is subtle yet real. For those who read both, the difference is difficult to ignore. The public story emphasizes continuity and growing knowledge. The technical record is more cautious, leaving questions open that public statements do not address. In that space between the two, skepticism naturally grows, not because of concealment, but because facts are filtered through different lenses, one designed for general audiences and the other for specialists. The result is a communication gap, and within that gap, the real debate takes shape. In laboratories chilled to nearly -200 degrees Celsius, vacuum chambers hold comet ice analogs made of water, carbon dioxide, carbon monoxide, and methanol. These samples are layered and bombarded with cosmic rays. For decades, astrochemists have tried to reproduce the surface conditions of objects drifting through interstellar space. The results point to a slow but relentless process. High-energy particles and ultraviolet light break molecular bonds, rearrange atoms, and gradually rebuild the ice into new chemical combinations. Over millions or billions of years, the surface chemistry evolves. Carbon dioxide can accumulate as water molecules are split and oxygen escapes, or as carbon monoxide is oxidized by traces of atomic oxygen. In laboratory experiments, these processed ices show a clear trend. Given enough time and radiation, the carbon dioxide to water ratio increases. The change is subtle over short periods, but stretched across interstellar timescales, the balance can shift dramatically, sometimes by an order of magnitude or more. When astronomers examine the spectrum of 3I Atlas, these experiments provide a plausible explanation. The object may have spent vast spans of time between stars, its surface steadily altered by cosmic radiation until carbon dioxide became the dominant volatile. This idea is not speculative alone. Published studies demonstrate that simulated interstellar ices exposed to prolonged high-energy radiation become enriched in carbon dioxide relative to their initial composition. The laboratory numbers do not perfectly match those of 3I Atlas, but they fall within a comparable range. Cosmic ray processing offers a way to produce water-poor, carbon dioxide-rich surfaces without violating known chemical or physical laws. Another explanation lies in the fundamentals of planet formation. In the disk surrounding a young star, temperature decreases with distance. Each volatile freezes at a different point. Water requires warmer conditions, while carbon dioxide can condense farther out. If 3I Atlas formed beyond the water ice line but within the carbon dioxide ice line, it would naturally incorporate more carbon dioxide and less water into its structure. Models of protoplanetary disks predict a wide diversity of compositions depending on where and when objects form. A body born in a carbon dioxide-rich region and later ejected into interstellar space would preserve that chemical signature for billions of years. Neither explanation is flawless. Laboratory results depend on precise ice mixtures, radiation doses, and timescales. Ice line models rely on details of disk chemistry and migration that are difficult to confirm for a single object. Still, both scenarios are grounded in physics tested on Earth and supported by observations of other comets. The carbon dioxide dominance in 3I Atlas is not impossible. It is simply rare. Peer-reviewed papers avoid declaring a breakthrough, but they identify these natural mechanisms as the best explanations available so far. The chemistry may be extreme, but it is not beyond imagination. The real test comes as 3I Atlas moves closer to the Sun. if its composition shifts or its activity pattern changes. Those developments will test these models in real time. The upcoming observation window, as the object passes its closest approach in December, represents the last major opportunity to watch the chemistry evolve before it disappears into deep space. For now, laboratory experiments and theoretical models offer the strongest guidance. The data collected in December will either resolve the questions or open an entirely new chapter. December 19th marks a decisive moment. That is when 3I Atlas reaches perihelion, about 1.8 astronomical units from the Sun afterward. Its hyperbolic trajectory will carry it out of the solar system, never to return. Every telescope with a viable line of sight is scheduled. The James Webb Space Telescope is set for another round of spectroscopy to capture any changes in the coma as the object swings past the Sun. Hubble is conducting an ultraviolet campaign to probe gas composition, focusing on sulfur and oxygen emission lines. Ground-based observatories are coordinating nightly observations, racing to record every fluctuation in brightness and every change in tail structure. The urgency goes beyond curiosity. It is about finality. Once 3I Atlas moves beyond roughly 2 astronomical units, the window for high-precision spectroscopy closes. The object will fade rapidly, slipping beyond the reach of even the most powerful telescopes. JWST's post-perihelion observations are a last attempt to compare chemistry before and after closest approach. Hubble will track the object as long as possible, but the signal will soon vanish into background noise for any spacecraft that might cross the tail. This is a single opportunity. There will be no second chance. The December campaign is not routine. It is the final chance to answer questions that have lingered since the first spectrum arrived. Does the carbon dioxide dominance persist as the comet warms? Does water ever become the leading component? Or is the chemistry fixed by ancient processes? Do new volatiles emerge as surface layers erode? Or does the spectral fingerprint remain unchanged? Only real-time observations can resolve these questions, and time is running short. Observation schedules are packed with contingency plans. If weather interferes in Chile, the Very Large Telescope shifts to backup targets. If Hubble encounters technical issues, ground-based teams scramble to compensate. The risk is not merely losing a night of data, but losing a once-in-a-lifetime event. By January, 3I Atlas will be outbound, its coma shrinking and its activity fading. For practical purposes, December is the only period when its chemistry can be studied under maximum solar heating, when outgassing is strongest. Every instrument, every hour of data is a hedge against permanent uncertainty. Ultraviolet observations aim to detect faint traces of sulfur, oxygen, and carbon that could distinguish between competing models. JWST's infrared sensors will dissect volatile ratios, searching for shifts that might reveal hidden layers or buried ices. Even amateur astronomers remain alert, hoping to capture last-minute changes in brightness or tail shape. The entire observing community is working against the clock. After December 19th, the questions harden into the permanent record. The object will fade, spectra will thin, and the opportunity to resolve the anomalies will disappear with 3I Atlas itself. Whatever remains unanswered in this window may never be answered at all. At this moment, the world's most advanced instruments are collecting data that even experts struggle to explain. As the gap between official statements and peer-reviewed results becomes more visible, public trust in science is tested. The mysteries of 3I Atlas challenge our models, our communication, and our willingness to question assumptions. In science, unanswered questions are not failures. They are invitations. Who chooses to keep asking will shape what comes next. What do you think the data is trying to tell us?